but don't neglect taking the integral, because you could run into anything. You could run into the antiderivative of exponents, you could run into inverse trig, you could run into some of the other techniques that I'll be teaching you, substitution, you know, kind of that engineering and completing the square to make it work stuff. So also get used to punching them in your calculator when it's indicated in the book. For some reason, yesterday I thought of snow kittens. I have no idea why, but today we have snow kittens. So I'm out of pictures, I think. I may have one more set that Morgan sent me of someone, but send me pictures. Okay, so so many things that when I was in calculus, you know, just sort of disturbed me, like, whoa, I already know how to do that, do I? You know, like, if it wasn't geometric, I didn't realize that no one could find the volume or the area of it. So you are elite in that area now, no, area, literally. You're elite already in the fact that you can find the area and volume of regular state objects, because other people can't do it. They have to have a geometric figure. So if you hold up something like a football and said, find the volume of that, they want to go throw it in some water and find displacement or something. But you could do it. You could like write an equation that is whatever maps the side of the football, and then you could revolve it around an axis. We'll talk about that later. So anyway, this, you know, one of my professors came in. That's going to bother me. Is that going to bother you? Okay. Okay. And drew like this, you know, something like this on the board, and said like maybe this is 1 and this is 3, and gave us the equation of it and said find out how long that curve is. Okay, I started pencil to paper, and then I thought, I have no idea to do that. And like, that is so disturbing that I can't find out how long that is. And also I realized somebody can, but it's not me, and I'm about to learn another thing that other people can't do. And remember how we're doing these things by magic. You know, as you enter calculus, you're finding the slope of a line at a point, which is technically impossible, but we use limits to make that happen. Many times you forget the theory behind the trick. The area and volume are all based on a Riemann sum, that all of a sudden you take a limit at the very end and take the number of items in there as it approaches infinity. And so all those rectangles become infinitely thin, and you're adding them all up. There's 1 day and a half, I think, that I actually took you through the long haul of that, where I went on and on and on with the sigma. And at the end I took a limit and I got an answer. And then I blessed you with the fundamental theorem of calculus, but you can imagine how fundamental that was. So don't lose sight of what you're doing and how powerful your superhero cape is the limit. You're taking a limit as 2 points come closer and closer together to find rate of change in an instant. You're finding the limit is the number of items between 2 finite places approaches infinity, and you're adding all of those up. It's really bizarre, and it works. Which I guess I'm going to show you another day. It's kind of, well, I don't know, today's a good day for it. Alright, anyway, I'm like, I started to write down how long that was, and I realized I can't find it. So, suggestions. How will I find out how long it is? I could get like a big spool of string, and I could like try to like, you know, stick it onto that with some glue, and then take it off and stretch it out and measure it. But I was saying somebody knows how to do it, because they build roads, roller coasters, all sorts of curvy things. A lot of you probably skied Hunter Mountain before, and if you look at the lodge, has like a scalloped edge that some engineer or architect has designed, and I think they already knew how long it was going to be before they ordered the material. I hope. Do y'all see what I mean? Like, gotta be a way to find that distance without somebody. I mean, you just gotta know ahead of time, I guess is what I'm trying to say. So how can we find the distance of that funny shape? This one over here on the left. What would you do if I said to find it? Grace?
We like, wait, no.
Grace?
Okay. Take the integral, like adding up the differences between all the x's.
Yes. In what way? The differences in all the x's. That would be, if I'm hearing, I don't think this is what you mean, but what you're saying is these are my x's. So I don't really know the differences in my x's, adding up all of those is gonna help. But I think you're on the right track. Emily?
This is like really dumb, but can you? No, never mind. It doesn't-
Say it.
If you take the values of the x and then if you find the area, you know the x, then you use the y. I don't know.
Yes, you do sort of. Something about
It's
that.
like if you take the area under the curve, and then you know how far you get on the x-axis.
You probably could do that. It's some sort of a perimeter thing. You know how you know the circumference of a circle? So you probably could do that. There's something easier. I never tried that. But you also said some words that are gonna be key in just a minute. Anna, were you going for the perimeter?
I was gonna say, yeah, like, if you made any sort of, like, object, and then you, like, work backwards to find, like, the perimeter.
Because you remember what happens when we take, that might work, girls. I think it would be very cumbersome, but, it's a great idea. It'd be interesting to see if it works and you found something new, the two of you. That may be easier than I think. I hadn't tried it before. In fact, you're the first two people to suggest it. But it is interesting. If you think of the, derivative of a circle, pi r squared, you get, 2 pi r, you get the circumference. So if we somehow could get and if I take the derivative of 4/3 pi r cubed, which is the volume of a sphere, I get 4 pi r squared, which is the surface area of the outer rim of that sphere, the balloon material. And so maybe we could do that. Find the area of it, take the derivative, and it would give us the perimeter. It should work. There's a little bit easier way though, I think. So yeah. Did you have an idea?
I thought that since to find the area we take the derivative function. Never mind. It was kind of going along with
The same, okay. Something easier. Find the length of that.
Triangles.
In what way?
You would have to like draw like, well, I mean, you would end up being like an integral, but you draw like a bunch of little lines on the curve and then use like dy and dx.
That's it. Say it louder, and then you what?
So you have to draw like it would end up being an integral, but
Right.
so
What was
like
the last
lines
two?
on the curve, so you use dy and dx.
There we go. And
And
y'all
you-
were sort of saying that.
Like a right triangle.
Okay, so this is what Carla's saying, I think. Correct me if I'm wrong. So if we make these into little lines, I'm drawing straight lines actually. In fact, let's use this tool. So what we're doing is we're banking on the fact that something's locally linear. So I actually pulled the line tool so you can be convinced that I'm using it. Now, if I zoom in on that, we would see that the curve differs a bit from the lines. However, it can make the lines infinitely what? Small, and then it would make the curve, and we can integrate, we can add up all of those lines. All right, so you also, a couple of you have started leaning into this dy over dx. Is that sort of what you were saying also, Carla?
Yeah.
Okay. So she's finding the slope, isn't she? Rise over run, rise over run, rise over run. And a couple of y'all have said what I'm gonna do. I'm gonna actually kind of blow it up for a minute, like I'm gonna go from there to there, which is a really bad idea, right? I don't wanna just like do this, do I?
No.
I don't wanna add up just those 3 lines, all right? But I could come closer and get a better idea of what's happening. And y'all see as I get closer and closer and closer, it gets better and better and better?
Yeah.
All right. And so I definitely can add up the distance between each little component. So let's go from this purple to this purple. All right, I'm gonna call this point x2, y2, and this point x1, y1. Because we're gonna have them all along here, right? We're gonna be finding the distances between those. So can I find out the length of this? Using the what formula? The distance formula. It's the square root of x2 minus x1 squared plus y2 minus y1 squared, and then you put on your superhero cape and add them all up from wherever you're going, A to B. So it like then starts to click through, starting at A, and in infinitely small increments it finds the next one, the next one, the next one. It's going like from 1 to 3 like this, 1 to 1.00001, because the limit is built into this fundamental theorem of calculus that works for us. Okay? All right, now the reason that I was listening so much to what people were saying, and Carla ended up really stating it, was a dy over dx is happening, and isn't that your, I don't know if you've ever drawn all this together. I love drawing all the mathematics together in AP Cal, but if I actually am doing the distance formula, I'm actually doing the Pythagorean theorem, and I think a ton of y'all realize that. If I'm going to go from here to here, isn't that dx? And this is dy, and I can do the Pythagorean theorem, a squared plus b squared equals c squared, and so that gives me dx squared plus dy squared, and so it's really just your little triangles of Pythagorean theorem, but it's also the distance formula. Everybody okay with that? Okay, so now I'm about to change this, but everybody remember this, okay? In fact, remember the next statement, because when we get into polar and especially parametric form, I'm going to want to leave it like that. But today I don't want all those x's and y's swimming around, because I feel like that I'm not in multivariable calculus yet. Okay, so we're in calculus of a single variable. And so we can deal with multivariable a tiny bit with implicit differentiation. But if you had to integrate like something with an x and a y in it, I'm not going to be that teacher that teaches you to do that. Okay? So what could I call that? Couldn't I just call that the change in x? Dx? And we can call that the change in y. But something's kind of weird about, like, this setup's not okay. All right? I know that a lot of times we can get lazy and not putting this in the back of it, or f of y dy, or f of t dt. But if I'm trying to add up something over time, if time's not changing, I'm not doing anything, okay? I need that little, you know, and if you're doing volume, it's the little bitty width of that penny disc, paper thin Pringle, or whatever you're talking about. You see, it's that third dimension that's happening. And so I kind of need that. I desperately need that there. Because right now it's not moving along the line like Grace said. Okay, so I need to make it move. Also, it makes it very user-friendly. So this is one of the few times in Cal 2 that I'm showing you where the formula came from. You know, I said I normally wouldn't be doing that. So somebody, don't know who, decided to divide this all by dx squared. And I can't just introduce that without balancing it out in my formula that I already have. And so with that, balance it out with the dx. Technically the absolute value of dx, because what's the square root of dx squared? Absolute value of dx, but dx, so you're moving to the right. And so it's a positive motion. Okay? Everybody all right so far? All right, so it's just balanced. And now I think everybody in the room would do this. This is so silly. Okay, so I have the integral from a to b of the square root of 1 plus dy over dx squared with a dx on the back. So I have the integral from a to b of the square root of 1 plus y prime squared dx. Super easy formula. That will find the length of an arc. Okay, now let me pause for a minute. Today what we're studying is arc length. And in honors pre-cal you learned, and maybe in physics also, you learned a little arc length formula. S equals r theta. I hope that rings a bell to you. It's like what you girls were talking about. It's like you could find the area of a sector in pre-cal, and then you could find the edge of that. Like it's the pizza and then the crust. Or the orange slice and then the orange peel. But girls, that's talking about just circular arc length. That's not what I'm talking about today, okay? So this old arc length formula was talking about if you had a sector, and it was talking about a piece of the circumference of a circle, okay? And that's not what we're talking about. We're talking about something that's off-road, however long it is, wherever it's going, we can find it. Does that make sense to everybody? So it's very powerful. All right, so super easy formula. It's on your study guide if you're starting to look at that yet under topics. It's in your book, super easy. Now, one other side note. Sometimes it's really hard to do in terms of X, and I hardly ever do this, and they hardly ever ask me to, but it could be that you want to take the square root of 1 plus dx over dy squared dy. That also works, okay? Now this is the derivative of, it would be an x equals 3y cubed kind of thing. Do y'all see what I mean? You could, there are functions that I look at the change in y with respect to x instead of the change, I'm sorry, I just said that wrong. The change in x with respect to y. For instance, if I have this one, x is equal to y squared plus 4y plus 7. Girls, I can't solve that for y. I cannot find a dy, well, I can find a dy over dx. But if I'm making an xy chart, I actually am doing this, where y is all of a sudden the independent variable. Do y'all see if I fill in 0 for y, I got 7. If I change y, then I get 12. Do y'all see what I mean? Now x is changing, I have a dx dy, not a dy dx. What do my limits of integration need to be? Why didn't I say a to b? Yes, and so on this picture right here, I could write the, I don't have the function yet, I'll show you one as an illustration. But say if I have this equation as a y equals f of x, then I'm going to use that form that I wrote down there where you have the square root of 1 plus f prime of x, or y prime quantity squared dx, and my limits of integration are going to be 1 to 3. But if I decide to do the integral of the square root of 1 plus f prime of y squared dy, then I need to know the y values because now I'm climbing up a different way. I'm going dy dx, dy dx, like this. Alright? So I'm climbing, so I need to have my limits of integration match my variable. Alright, so let's do some. So I'm in your book, if I know you don't have your book with you, but if you ever want to look back at the examples I'm doing, they explain all of that in chapter 7, section 4. And I'm going to do example. Let's just go ahead and do this kind of tough example 2. All right, so on page 480, if you want to refer to your textbook, which I think is a really good book, 480. All right, so this is example 2 on page 480, but you can just follow along. It says, find the arc length of the graph, y equals x squared over 6, plus 1 over 2x. More than likely, they would give you a picture of this. Without a calculator, it'd be really hard to know what this looks like. It has a vertical asymptote at 0, by the way. If I really had to graph this, girls, without a calculator, I would get a common denominator, and I would go back to all my rational function stuff. Look at the degree of the top and the bottom, and you've done that before. The portion that we need, they want me to do it from 1/2 to 2. And so they have it drawn like this. If I get a common denominator, I don't think it even has a slant asymptote. I think its end behavior model is really parabolic. But anyway, they give us a little picture of it from 1/2 to 2. So we're finding that arc length. That didn't drop very well. It's really kind of going through this dip right here. Okay? But I can find the length of any piece of that they want me to use in the formula. Alright, so I'm going to take y prime, which gives me 2x over 6. Are y'all okay with x over 3? I'm going to write this as x squared over 6 plus 1/2 x to the negative 1. bringing that x to the negative 1 up, I bring it down, and I get minus 1/2 x to the negative 2. And so my first derivative is x over 3 minus 1 over 2x squared. You could have gotten a common denominator, but then you have to use the quotient rule, which I don't really want to do. Okay, so now, your formula that you'll be memorizing, you're doing the distance formula like some of you were suggesting and that Carl really landed on. And so you're gonna have the derivative squared. I'm gonna do this in terms of x. I'm gonna go from 1/2 to 2. This is easily done in terms of x. My formula was already solved for y in terms of x. So I'm getting the dy dx right here. All right, so I'm gonna put this in, x over 3 minus 1 over 2x squared. And I see that there's a chance this would be a non-calculator problem, so let's keep going. Because now I'm going over some integral techniques that you need to see, and then I expect you to be able to do. All right, so you have 1 plus, I've foiled that out off to the side just to make sure I had it right. And this gives me, whoa, I did something wrong. I'm sorry, I copied it wrong. Sorry, girls. This was x to the 3rd over 6. So I'm glad I noticed it. I guess I could do this one also, but I don't know what it looks like. So this was x to the 3rd over 6. And so this would be 3x squared over 6, or x squared over 2. Because I really want to do the one that they gave us because of what happens to it. X squared over 2. Okay, now pause for a minute. You haven't done this very much, this engineering of things to make them be able to factor. But when you start to see stuff that looks that much alike, something's going to happen with your FOIL with those 2x squares. Like, be aware that you've seen that right now, okay? And so this was x squared over 2. Okay, so I FOILed that out, and you can see in the front I would have x squared over 4. In fact, it's probably good for us to do it. X squared over 2 minus 1 over 2x squared. I've seen this to where I'm suspicious something interesting is going to happen.
You would have x to the 4th over 4, right?
Thank you. Keep correcting me. Okay. All right. Thank you, Carla. X to the 4th over 4. What's going to happen there? You're going to get minus 1/4, aren't you?
Yeah.
Because your x squared you're going to cancel? Well, I've said that. I probably shouldn't say it on video. When I got diagnosed 5 years ago, a little more than 5 years ago, and so I was in treatment 5 years ago, I never looked up my cancer. Like, never. Like, I didn't want to know. I didn't want to Google it. You know, it's the worst thing you could ever do, by the way. So I just I don't want to know. I'm just going to fight it. Last night somebody was asking me about it, and I thought, I wonder what my survival rate was. So I looked it up, and that would be alive 5 years later was a 5 to 40% chance. So anyway, back to canceling. But isn't that awesome? That's great. So here I am 5 years later. All right. So anyway, I'm glad I didn't know that going into it. This is x to the 4th over 4. This is minus 1/4. Minus 1/4 is minus 1/2. And this is plus 1 over 4 x to the 4th. And we have dx. Looks really bad, okay? So I'm going to hang with it though, because here's how you learn this. I saw that did something weird like this, okay? And now I'm going to subtract the 1 and the 1/2. I think you would also. 1/2 to 2. And if you were not expected to be able to do this, I wouldn't be going over this right now. I'd be doing some other things. So these are techniques you really need to know. 1 minus 1/2 is 1/2 plus 1 over 4 x to the 4th. And if they won't let me have a calculator, I'm still like plowing away at it. This would be non-calculator. But I'm thinking to myself, something similar to that just happened to me, didn't it? All right, so I'm going to factor this. Notice that I put my constant in the middle on purpose because I think I'm going to create that. So I have the square root. I'm going to make this x squared over 2 plus 1 over 2x squared, trying to follow what just happened to me with the plus sign. All right, x to the 4th over 4. What is this going to give me? plus 1/4 plus 1/4. So I get plus 1/2 in the middle. Again, that's why I keep saying really do your homework. You have to fight with this stuff mentally. Okay? So this gives me 1/2 to 2. Are y'all okay if I just land here? I don't like red. This is x squared over 2 plus 1 over 2x squared. A lot of all I've done since I set it up was algebra. The only calculus part of this problem was I took the derivative at the first. Everything else is algebra. That's really ugly, but it says x squared over 2 plus 1 over 2x squared. Alright, so I want to rewrite this for myself. X squared over 2 plus 1 over 2x to the negative 2. So when I integrate this one, it's going to be x to the third over 6. When I integrate this one, my coefficient is 1/2. And I add 1, I get x to the negative 1 over negative 1. From 1/2 to 2. So now my arithmetic's gonna, I hope it doesn't get me, because now I'm finally through with the algebra and now I've got this ugly arithmetic. Alright, so when I fill in 2, I get 8/3 minus 1 over 4. This is minus 1 over 2x.
Yeah.
It's over 6.
Oh goodness, thank you.
Not over 3 in the middle line.
Thank you, thank you. Thank you. Alright, that should be x to the third over 3, but there's already a 2 down there, x to the third over 6. So then I was going to miss it after that. Alright, so then when I put in 2, thank you, I get 8 over 6 minus, I hope, 1 over 4. When I put in 1/2, I get 1/8 over 6, which is 1 over 48. And when I put in 1/2 here, I get minus 1/2, and then I have, I'm going to put it over, it's minus 1 over 2x, and then for x, I put 1/2. So do you see that cancels and I just have minus 1? So you can figure that out. You got to be careful with it. All right, now I understand that I can reduce this one right here. I see that I can reduce that one to 4/3, but I kind of don't want to. I'm going to stay with this 48 scenario as I kind of back away and look at it. So if I make it all over 48, multiply that by 8, I get 64 over 48. Multiply this by 12, I get 12 over 48, minus 1 over 48, plus 48 over 48, if I don't have a calculator. I don't know what that is. I think it's 99 over 48, possibly? 64 minus,
Yes, 99.
is it 99?
Yeah.
And those are divisible by 3, so that's 33 over 16.
Wow.
Now, by now, you may have lost sight of what we even did. We found the length of that curve. And my only step in calculus was to take the derivative. Everything else was intricate algebra 2. Okay? Alright, so let's do example 4. Alright, so you don't really care because you may not look it up in the book, but we have y equals ln cosine x. We're going from x equals 0 to x equals pi over 4. Not really a parent graph. This you should know what that looks like. If you had to super struggle with it, you could probably figure it out. I don't even know if I could do it, but anyway, they've given us a picture of it, which a lot of times they'll give you a picture of it. It's not something just super normal. And ironically, it looks sort of like this. It has asymptotes. It looked like at pi over 2, yeah. Cosine of pi over 2 is 0, and ln 0 doesn't exist, so there's these asymptotes here at pi over 2. Alright, so we're finding the length of this curve right here. I might as well do it in terms of x, dy over dx. So here's our calculus, y prime. To remind you of the derivative of a logarithm, you say 1 over blah. While you're down there, you say ln of the base, but isn't it just ln e? And the derivative of cosine is negative sine. Well, what would you write down for that before you started your problem?
Negative 10.
Negative 10. Alright, so that's negative 10x. And so I'm going to integrate it from 0 to pi over 4 of the square root of 1 plus the derivative squared is your new formula. 1 plus the derivative squared. So this is great. This is the reason I'm like going ahead and finishing the problem. I've already taught you how to find arc-length. That part was pretty easy. The square root of 1 plus the derivative squared. Okay? But I'm also backtracking over lots of things that you need to know to pull off any kind of integral, anytime, anywhere. What would you do next? You have no calculator at this moment. What would you do next? What's 1 plus tan squared? Secant squared. And so if I take the square root of that, I have secant x.
Oh my god.
Yes. But my guess is, if you're like most of my students over the years, that you have not really super memorized those formulas yet. And the integral of sine you can do, the integral of cosine you can do. Yeah, go ahead, Sophia Gray.
ln the absolute value of secant x plus tan.
Yeah, it's very similar. You have to always know it from here on out. Thank you. It's very much like the derivative of secant is secant tangent, so that's how I remember it. Be careful that you read over these before tests and that you're trying your homework because there's minuses thrown in and all sorts of stuff. All right, so now I have a logarithm I have to mess with. The secant of pi over 4 is root 2. The tangent of pi over 4 is 1. Don't neglect filling in 0. The secant of 0 is 1. And the tangent of 0 is 0. You should be good at that. ln1 is what?
0.
ln1 is 0, so that's just gone. And that's how long that curve is. And you couldn't do anything from that. It's 0.881 units long. Interesting concept. Don't forget that I always tell you what it is that you're doing. Suppose you're on one of my tests or the AP exam, and somebody asks you that arc length, and you get really fed up with it, and you've tried it, hopefully, and you can't get it. Look at how we've learned what we were doing. Couldn't you find that distance maybe, and at least estimate it if it's a multiple choice? So don't forget what you're doing, okay? All right, so I'll do a couple more of those in the next class, but that's all I'm going to do for right now. The first sheet of paper that I had. Oh, here it is. Okay, does anyone have a take one of these and pass it around. Does anyone have a specific homework question? I'm going to do some volumes for you. Celine?
49.
All right, this is 49 on your homework. Packets are coming around. And your other packet that I gave you, just always have them with you. Try to bring it in your notebook. What page is that, Celine?
Page
474?
465.
Oh, 465, okay. Oh, yeah, because that was the show, okay. 465, number 49. Okay, so definitely need to go to revolving around line. If you, I looked at the views. Of course, I can't tell if you personally watched it or not. I maybe should have held you a little more accountable.
You should
And
always have to comment on it or something.
yeah, like
You should say that this was
Anna
a
so
special
far is the
word.
only one that commented. Did you get
I
mine?
know.
I'm like, well, somebody commented on my video. I think it was more a comment on the picture than on my expertise at
No, I commented for a video.
Thank you.
You should like say it like a secret thing halfway through
Oh, I should.
at like a random point,
Yeah.
so that like
Your
it
friends
says
are now going to
comment.
The thing is, I watched them at double speed.
But it has to be like
You watched the one?
At double speed with the subtitles on, so I like read it.
Okay, good. Yeah. And I sound a little more normal that way anyway. Yeah, do it.
That's because I like reading it.
Yeah.
That's what I do.
That's cool, good. Okay, whatever it takes. Hopefully it's very helpful. And so if Carla watched it at double speed, the 9-minute video only took her 4.5 minutes. All right, great, awesome. Girls, look, if you're, well, let me just do the specific problem. If you haven't watched Revolve Around the Line, I think it's 21 minutes or less, please do that, okay? It will help you, I promise. Alright, so I have y equals e to the negative x squared over 2. Y equals 0. X equals 0. And x equals 2. Everybody verify that I've actually got the right equation. Alright, so determine which value best approximates the volume. Oh, I thought it was going to say something else. I'm sorry. Which value best approximates the volume of the solid generated by revolving the region bounded by the graph of the equation about the x-axis. Okay, so they're getting you to estimate. Alright, what in the world does e to the negative x squared over 2 look like if I'm demanding that you graph these, and I'm going to do it without a calculator, I hope. E to the 0 is 1. If I put in 1, I get e to the negative 1/2, whatever the square root of e is. I think you would need a calculator here. I'm not sure. It's an even graph, and it's exponential decay. There's probably a piece of it over here.
No, it's like.
If I fill in 2, I get e to the negative 2. 1 over e squared is 1 over 0.693, whatever that is.
It goes like this.
It goes, does it go back?
It looks like this.
Okay, do it again.
Like, it's like.
It's
like
a
that.
little, it's like a little bell curve, but like
Oh.
a little more flat.
Like that? Okay. And we're going y equals 0. X equals 0. This is one they would give you when I think about it. And 2, is 2 out here? Like, is that 2? Where is it on the bell curve?
It's like something like that.
I can't believe in bio we did stat, like we did statistics.
We're doing stat
And all of the people in stat failed actually.
We're doing stat and right now, and so we didn't
We were doing it, I got a 2.5 out of 5. I got a 3 out of 5. But we were right.
Is it negative x squared over 2?
Yes.
Yeah, I think they would let you give you a graph of this or let you have your calculator.
Because like the week after I got some like chocolate fondant, and now it's just not going out. Even if I like take toothpick, that's what I was thinking like users and tablets and with like using rubbing off portions. It's just not coming out. So there's like forever like muffin in my costume.
Alright, so if I did this rectangle, this is 2 and this is 1. If I did this blue rectangle, oh, but we're doing volume, we're not just doing area. So if I did this, and it gets really close to 0 at 2, and if I revolve it around, like just the triangular part, it's going to make a cone. The volume of a cone is 1/3 pi r squared h, I think. 1/3 pi r squared h. Radius is 1, height is 2. I don't think I've been oh. What's the answer, Celine?
I don't know.
Oh, I thought it was 3. I thought it was something small.
It's 2 pi the integral over 3, which is approximately. So we got that. It's 2 pi over 3, which is approximately.
Isn't that the volume of a cone, 1/3 pi r squared h?
Yeah.
Okay, so anyway, what I was doing was I was saying, what if I just went straight there linearly and revolved it around the x-axis and make a cone? These sort of cancel out and gives me 2, times whatever's left over, and so I pick the smallest one. I don't have any idea how they did it. Did anybody look it up on
I looked it
CalChat?
up, they didn't let you.
They did exactly.
Oh, good, good for
But
me.
then I was like, that's not what you're doing.
Yeah.
So like,
I don't remember ever working this problem. I guess I picked it out and thought it looked great, and I would work it later. So here it is. Sometimes I do that. Okay, Celine Rickman. Oh, and see, it's like a planet in the audience, because that just sort of fed right into what I was talking about. Don't forget what you're doing, and you can use it to estimate. I definitely would not have picked B. I hope you would not have picked B. It's negative. Okay, look real quickly at this. It's somewhere in your packet. Okay? Find this. It's on the back, Emily, is that right? Alright, it's on the back. I'm sorry, the thing we just got. Turn that over more, yeah. Oh, so y'all see it on your handout, on the back?
Yeah.
Okay.
Flipping over.
Alright. So, like I said, many times they give you a picture. If they don't, you have got to do a picture. You desperately want to make sure that you're doing it correctly. Anyway, they gave us this region, okay? And this is 6. This is 2. Alright, find the area. So A, if I want to find the area, this is the line y equals 6. And this is the curve y equals 4, ln 3 minus x. Okay. Now, to me, area is so easy, it's hard sometimes. All of a sudden, once I teach you volume, and the A part many times on a free response is just area, then you feel like you gotta throw in all these fancy pies and R squares and stuff. It's just area, length times width, okay? Of all these little Riemann sums. So to find the individual lengths of all my rectangles, I'm gonna do top minus bottom, okay? And so I have the integral of the top, which is 6, minus the bottom ln of 4 ln of 3 minus x dx, and I'm going to do this from 0 to 2. Always follow your variable. And then I think I punched this one in the calculator. I guess I've checked my answers on this. Or else I'll be set up somewhere. I don't remember where I got this problem. Right now, you couldn't integrate that. I haven't taught you how to integrate a logarithm. Hopefully, you can differentiate a logarithm. All right? So it'd be a calculator active problem, but that's my setup. Let's quickly go to B. All right, so B is going to be up here. All right, B is find the volume when it's generated along the line y equals 8. All right, so girls, this is something that I hope you heard in the video. Washers, awesome. If it's washers, I would strongly suggest, which I hope I did in the video, I just gave you one from another year. I strongly suggest that you go ahead and set up your washers, because sometimes you have to subtract within your washers. Okay? So what you're doing is you're taking an outside circle minus the inside circle so that you have a ring. Alright, now when I'm going up and over this way, I'm saying top minus bottom. If it's underneath, I'm gonna We'll just talk about all the different scenarios. You're going to square it, is the good news. You kind of can't mess it up. But anyway, I'm going to say this is going to be the outer ring, green, which is going to be 8 minus this curve. It's going to go up and over like that. All right? So this is going to be 8 minus ln of 3 minus x squared. And then the inside that I want to come and cut out is going to be right in here, which is just 8 minus 6. So you see I've got this thing that I'm going up and over, okay? And then I want to squeeze in the last part if I can. The very last thing says that you are doing cross sections. So now it's everything that I've taught you recently. Cross sections on the C part. Cross sections, it says, are squares. You see the word cross sections, you know what I want you to do? I want you to draw a smiley face. I was tutoring a girl in AP Calculus in Florida on FaceTime the other day, and I was drawing smiley faces on our cross sections, okay? When you see cross sections, go relax. I just have to add up a bunch of squares, okay? I'm going to go from 0 to 2, and the squares, the side is going to be created by 6 minus ln of 3 minus x. Are y'all okay with that? It's just like if I started slicing this book, and you can be packing up, but please listen to me, okay? Wouldn't rectangles start to fall off onto the cutting board? Girls, with cross sections, The figure's already made. You are not revolving to make a figure. Okay, with cross sections, you where somebody's handed you a 3D object to cut up, like food. Bye. I'll post your homework, it'll be on our plan.
I don't